Hey, good afternoon, everybody. My name is Chunyu from Tianjin University of China. Today, I'm glad to share my work here, and my topic is flexible capacitive pressure sensor and their applications. And the following three parts will be included: the background of flexible sensors, the methodologies of sensor improvements, and the results of my works. Okay, now let's begin the first part. As we know, sensing technology have facilitated our daily life and industrial manufacturing in the past few years, especially the acceleration of automation and further promotes the development of various sensors. But in some application scenarios, the stimulus is always applied to the object with irregular surfaces, and the conventional rigid sensors are difficult to use. So flexible sensors are proposed to address this problem. Among these flexible sensors, tactile sensors inspired by our skis have attracted more attention due to their abilities of tactile perception. Especially pressure sensors have been extensively studied due to their importances for wearable devices, human-machine interaction, and robotics. And recently, to achieve pressure perception, several sensing mechanisms have been proposed, including resistive, piezoelectric, and capacitive. All of them aim to fabricate sensors with excellent characteristics. And in my presentation today, I will only focus on how to improve sensitivities of capacitive pressure sensors. According to the governing equation of capacitors, the improvements of dielectric layers mainly contributes to the improvements of sensor sensitivity, such as introducing various microstructures to increase the change of the D, or using various composites with high permittivity to increase the change of epsilon. But the most reported sensors have to suffer from the attenuation of sensitivity when a high pressure is applied to this sensor. So designing a capacitive pressure sensor with a high sensitivity over a high pressure range is still a challenge. So we proposed a new dielectric layer to improve this problem. As shown in the schematic of my sensor, this new dielectric layer comprises two parts, including the high PDMS microcones and the short PDMX mixing CNT microcones. They were fabricated separately by a series processes and then assembled by in a square ring arrangement way. This arrangement of height and material enabling this dielectric layer with hierarchical microstructures and permittivity. This is the key of our sensor to improve the sensitivity over a high pressure range. And to explain the importance of this arrangement, we fabricated three types of dielectric layer. As shown in the left figure, and the right figures show the mechanical analysis for the first two dielectric layers. By introducing microstructures and composites, stress concentration and high permittivity gradually increase the sensitivity. But in contrast, the faster deformation leads to a decrease in sensor range, which means there is a lower sensitivity when a high pressure is applied to this capacitive pressure sensor. But in our sensor, this new dielectric layer comprise the two microstructures, and with a lower pressure, the high microcones will be compressed, thus increasing the capacitance. And because there is no contact between the short microcones and the dielectric and the electrodes, so the capacitance change of capacitor 2 is negligible. With the pressure increasing, the short microcones start to be deformed, thus lead to a high capacitance change. So increasing the sensitivity because of its permittivity. This generates compensation for the deformability decrease in of dielectric layers. So our pressure will exhibit a high permittivity over a high pressure range. To verify our prediction, we fabricate and calibrated these sensors. According to the results, compared with sensors proposing novel microstructures and permittivities, our sensor shows a 1.1% sensitivity when the pressure is below 20 kilopascal. And with the pressure increasing, the short microcoils lead a high capacitance change and enable our sensor with 3.2% sensitivity, which approaches threefold increase, although the pressure is beyond 30 kilopascal. The sensitivity of our sensor is still 1.0%. So these results demonstrate this square ring arrangement of hierarchical microstructures and permittivities plays a role in sensitivity improvement of capacitive pressure sensors, especially over a high pressure range. Besides, our sensor proposes a faster response and release time and a lower limit of detection. These merits provide a potential for real-time monitoring and tiny pressure perception. Besides, considering the importance of sensor ability, we attached our sensor on cylindrical objects with different curvatures, and we found when the curvature is 7 centimeters, the interface between the dielectric layer and the electrodes will break, which means our sensor can achieve conformal contact if the object curvature is beyond 7 centimeters. At the same time, we also recorded the corresponding capacitance change excited by different temperatures and pressure loadings, and we found our sensor proposes excellent stability and durability. At last, we also measured another sensor with the same dielectric layer, and identical performances further demonstrate this dielectric layer provides a new way for the sensitivity improvement of capacitive pressure sensors. To verify the practicality of our sensor, we attached our sensor on the rest of adult male to monitor the tiny ratio pulses. According to the capacitance change, we observed some periodical waveforms, and we can identify 3 peaks. And after the fast Fourier transforms, this signal shows a 1.14 frequency, which is equal to 78 beats per minute. These results are similar to the medical results, which proves our sensor can perceive tiny pressure. Besides, we also fabricated a keyboard cover, integrated our sensor to monitor the finger pressing. In the experiments, 2 volunteers pressed the keys of the keyboard, and we recorded the corresponding capacitance change. And according to the results, we found our sensor can perceive the differences of finger pressing from different individuals, which provides a chance for early privacy protection when we use passwords to unlock our computers. In conclusion, we fabricated a new dielectric layer to address the sensitivity attenuation and offers some demonstrations of their applications. Come here, that's the end of my presentation. If you have any questions or any ideas for collaboration, please contact my supervisor, Dr. Siyi. Thanks very much.